We are now recording. Let's get the slideshow set up from current slide. And we're just about ready to go. All right. Now, let me hit a couple of announcements. This first one is really important. I wish more of the people were here. As they come in, I'll repeat it. So I'm hoping they'll come in. This won't affect you directly, sort of indirectly a little bit. We have a SACS visit coming up, a reaccreditation visit. That's the Southern Association of Colleges and Schools. That's our accrediting agency for all the 2-year, 4-year graduate schools, all that kind of stuff in the Southeast. And we've got a visit scheduled from them sometime in about 2 or 3 years, okay? It seems like a long way off. Well, they're already now beginning to try to get all our data together because they will be looking at all the data from past years. So here's Eurosay. Okay, and here's Jared. And here is Andrew. And here is Alex. All right, and here is Hunter. Okay. Was there anybody else I missed? Okay. Okay. I was just saying before y'all came in, we have coming up at the college here what we call it, the title of it is a SACS visit. Now this is 2 or 3 years away, but it's going to be coming fairly soon. And you get Samuel here. All right. Anyone else come in since they called roll? Okay. Yeah, I got you. Yeah. You're the else for anyone else. Got you. Okay. We have a SACS visit coming up, and one of the things they look at, not just what happened in the last year or two, they look for several years back, which is now, okay? And our team has been reviewing things, and it seems as if our student course evaluations, the participation has been dwindling in the last several years, and that's not a good thing because SACS looks at those data pretty carefully. So I think we may have even dropped under 50% participation, where we need to be 80% or better participation. So the big push is now everybody do your student course evaluations. Has anyone done them already? All right, good deal. Everybody, please do your student course evaluation. Please don't put it off. It's all right to do it after you see your final grade. If that's going to influence it, that's fine. But just don't forget to do it afterwards. I just know when I was an undergraduate, once I had taken that last final exam, I cranked it out of school mode and was heading home, mentally or whatever. So it was really easy to forget. So I would say if that might be the case for you, go on and do it now. Don't wait till the end. Do it now. Okay? So please do the student course evaluations. All right. One other issue, and this is a minor thing, I don't think it'll affect many of you, but it might affect somebody. Normally on Fridays, I have office hours on the Birmingham campus, 7:45 to 11:45. Not this Friday. I've got an infusion scheduled for this Friday, so I will be at the Kirkland Clinic before 7 o'clock and won't be leaving there until probably after 4. So no way I'm going to be on campus at all on Friday. So if you need to see me before you leave on Thursday or any time up until then. All right. Any questions on any? Oh, let's go over what we're doing now, okay, and what we will be doing. We started last time in Chapter 6, Electricity and Magnetism. We're going to continue that. We'll do that for about the first 2 hours today, less than that now because we've already lost some time. And then we will have the lab. I think we'll cover enough material to have the first lab in the Electricity and Magnetism chapter. So we'll have that lab for the next 2 hours. and then we'll come back here to the classroom or go to a different class if you prefer, whatever, and we'll be there for the last 30 minutes taking the test on Chapter 4, heat and energy, okay? Heat and temperature, heat and temperature. Temperature and heat, whatever the name of the chapter was, okay? So, that's this thing for today. Thursday, we'll continue with Chapter 6, electricity and magnetism. Pretty sure by then we'll get enough for a second lab in this thing. And I doubt if we'll finish the chapter by then, because it's a fairly long chapter. But if we do, we'll still have a lab in the following Tuesday on especially the magnetism part, electricity and magnetism part. So that'll be Tuesday of next week. Somewhere in there, we will finish Chapter 6 and have our test in Chapter 6. Could be Tuesday, could be Thursday of next week. And at some point, we'll start Chapter 8. We don't do 7, we'll do 8. And Chapter 8 is the one chapter on chemistry we'll do. It's just going to be basic type stuff in chemistry. And we do have a lab in that. It's just a paper lab. It won't be anything you have to do in the, mixing chemicals or anything. It'll just be what I call a paper lab. And then once we're through with that, we will have a test in that. Now that may not be during a class day. That may be the final exam day. The odds are it will be. So your last day here, which is a Thursday of finals week, Tuesday we have class, and then if we haven't finished everything, or if we have whatever our situation is in, we'll talk about it when we get closer, then Thursday is the finals. The odds are we'll have our last chapter test, the Chapter 8 test that day, followed by the final exam. Final exam will probably be the shortest and probably the easiest test you've had all term, okay? So it won't take you very long, and so the Chapter 8 test will be right before that. You'll easily, I think, do that in 30 minutes too. So I won't have you much time on that last Thursday. Now, let's back up from that. How are your other exams? When are you through?
Non-existent.
Huh?
Non-existent.
You don't have any?
As far as us,
Okay.
yeah.
So is that all you've got that last week?
Thursday. That last Thursday. Can't remember what day that is.
Okay. Well, I'll
Wednesday. Wednesday is our last.
Yeah. Okay.
Our last exam.
Okay. What I was wondering is that might not be the case for you. So what I'll say is, once we're finished with class on that Tuesday of finals week, once we're finished with that class, and by the way, that day I'll be returning every lab and test that you have turned in up to that. I think I've returned a few things to you so far, but there's somebody, not always the same body, but somebody hasn't turned in something in just about all the labs and all the tests. I'll go through those when you're doing things today to see if I can return anything to you. But anyway, I'll return everything to you that Tuesday, a finals week. That's two weeks from today. Okay? After that, and we finish everything we do that day, which may be before the 4.5 hours is over. After that, anytime you want to take that last chapter test and the final exam, you can. You can take it that Tuesday if you want. You can take it anytime Wednesday, or if you want to do it after your last final on Wednesday, before your last final on Wednesday, whenever you want to take it. Or you can come in and take it regular time on Thursday. You can take it Thursday morning. You can take it any time after that last day of class. I won't make you come back just to take a fairly short final. So if you want to plan to do it earlier, you can. And remember, you can have a formula and equation sheet on that last chapter test, well, on the one today, on the one on Chapter 6, which will be sometime next week, and the one on Chapter 8, and the final, you can, every one of them, you can have a formula and equation sheet. All right. Any questions? All right. Where we left off last time is in the text around page 141, if you have the new edition. It's the electron theory of charge. And I'm pretty sure that we got, I don't know. I don't remember that we did anything on this slide, did we? I was thinking we got started on it, but I don't.
I don't think we did.
Okay, so let's go from here. The last slide we did was that one. Yeah, that's the one we did. Okay. I thought we did one on this, but here's the one on electric charge. Okay. Remember, the last slide was talking about the smallest entity that an element can exist in is an atom. For a compound, it'll be a molecule, okay? But those are both very, very tiny entities, okay? Now, in that entity, in that atom, let's go to the atom first, the one we talked about, it has a nucleus, which is incredibly tiny, but incredibly massive. Its density is almost unbelievably high, okay? Now, it's surrounded by a cloud of electrons which have almost no mass at all. Their mass is about 1/10,000th the mass of a proton or a neutron. Really, really small. But they take up almost the whole space or the area, the volume of that atom, okay? So basically, most of the volume is occupied by very little mass. And all the mass is concentrated in that tiny little nucleus in the middle. So the protons have a positive charge, electrons have negative charge, neutrons have no charge. And any other particles you find there, we won't get into those. We'll just leave it like that. So, where are these charges in matter? These are inseparable properties of certain particles, i.e., the protons are always positive charged. You'll never find a proton that doesn't have a positive charge. You can't separate the proton from the charge or the charge from the proton. It's part of the proton, a single positive charge. The electrons, which, like I said, are 1/10,000th the size, the mass of that proton, still have the same charge, only it's a negative charge. And you can't separate the electron from the charge or the charge from the electron. So they carry the negative charge. Protons are the positive electric charges. Cannot separate them. Okay? Now, how do these charges interact? They interact through something we call electric force. Okay? Force is a push or a pull, and these could be either, because like charges repel each other and unlike charges attract each other. Two protons, what would they tend to do? Repel, because they're the same charge. A proton and electron? Attract, because they're opposite charge. Two electrons? Repel, because they're opposite, the same charges. Okay, so like charges repel, unlike charges attract. Hang on to that, because we'll see almost something very similar to it in magnetism. Now, not all materials are neutrally charged. This table is, I pretty much am, the board is, pretty much everything is neutrally charged, but not everything, okay? Something that has a net charge is no longer an atom or a molecule, it's now an ion. An atom or a molecule, by definition, has a neutral charge. Same number of protons as it has electrons. So the charges are balanced. However, if they get out of balance, that becomes an ion. A non-zero net charge, either from the loss or the gain of electrons. How about protons? Can a material gain or lose protons? What do you think? No way. The proton is part of that nucleus, way down inside, very tightly hung together. Then no way it's going to lose a proton. To lose a proton, you have to have a nuclear reaction. Let's not have any of those, okay? We don't want to have any nuclear reaction. So how they get charged is either by picking up an extra electron or losing the spare electron. Then it would be negatively charged if it picked up an electron, positive charge if it lost an electron. That's the only way you get ions. I think we mentioned before the gas that flies up and down in these tubes those are ions. It's a mercury vapor, I think is what it is in there, and it's been charged either positively or negatively, and then they fly back and forth in the tube, and they're flying past excites energy in the coating of those tubes, and that's what gives us light. Okay? But those are either gained or lost electrons, never gaining or losing protons. That's a nuclear reaction. Not Jared, but Jared. Okay. Now, here is a sample of a neutral atom. This happens to be, they don't tell you this, but it happens to be lithium. Now, how do I know it's lithium? 3 positive charges in the nucleus. And if you look at the periodic table, and if you have a regular book, that's the back of the last cover page. Okay? Number 3 is lithium. Over here, first column, second row, right beneath hydrogen. Okay? 3 protons. To be a balanced atom, neutral atom, that has 3 electrons. And they've drawn this pretty nicely. We'll be doing more of this in the next chapter. Okay? Because the innermost shell, electron shell, can only hold 2 electrons. Only 2. Any atom you happen to have can have no more than 2 electrons in the inner shell. Hydrogen is the only one that only has 1, because it only has 1 electron, and that would only have 1. But everything beyond hydrogen has 2 in the inner shell. And since it has a total of 3, the third one is out here. Well, that one out here is really isolated. Okay? The nucleus is way down in there. That inner shell, those 2 electrons are floating around it, and that one's sitting out there almost by itself. Okay? And it's really easy for lithium to lose an electron. If it does, what would it become charged?
What?
If lithium were to lose an electron, what would its charge become? Plus. A plus charge. It would now be not a lithium atom, it would be a lithium ion, because it has a non-zero net charge. Okay? And by the way, since we'll be covering this in the next chapter anyway, everything in this first column here, and that's why they put the table together here, has one of these single electrons in its outermost shell. That's all that's there. 1 single electron in the outer shell. All these tend to lose those electrons pretty easily. And therefore, hydrogen, lithium, sodium, potassium. We don't usually run into much rubidium, cesium, or francium, but those top 4 are very reactive. Except for hydrogen, we call them soft metals. Very reactive metals. You hardly ever see hydrogen or any of these by themselves. They always combine with something. Even the second column, beryllium, magnesium, calcium, they also tend to react, but they lose 2 electrons from the outer shell and become +2 ions. These become +1 ions. Okay. That's a little more chemistry than it's calling for here. Now the next slide, or next part of this slide, is not quite accurate. I know what they're trying to do. They're trying to illustrate. Oh, no, I'm sorry. This one is. So that positive lithium ion has lost an electron. Something that came along, let me suggest to you what came along, more than likely something from column 7. Column 7, fluorine, chlorine, bromine, iodine. You could have one of the other 2, but usually not. Okay? If one of them came along, they have 7 electrons in their outer shell. And their outer shell loves to have 8. So they're hungry for 1 more electron to make them have a filled outer shell. You see, when this loses an electron, it has a filled outer shell. It's that 2 in there. And all the others here, if they lose that outer electron, their next shell in is completely full. And that's when an ion is happy as it can be. Okay? It's when its outer shell is full. So if one of those came along, they would rip off this electron from the lithium, and then they become what charge? Negatively charged. The lithium would be positively charged, and then they form a salt, a lithium chloride, lithium fluoride, lithium bromide salt, and those would be, and by the way, if you had sodium, lost its outer electron, became positively charged, it combined with chlorine, which gained that extra electron, became negatively charged, then they're held together electrostatically, unlike charges attracting each other, and they become a very strong compound of sodium chloride, salt that you salt your food with, that are probably on your Pringles, right? Yeah, okay. What's that? Okay. So, that's what's happening here. That's a very realistic picture, losing that outer electron, becoming a positive ion. Okay? This is the picture that's not very reasonable. They show that same lithium atom, though they don't call it this, picking up an extra electron. It doesn't happen. Not to lithium. It does to fluorine and chlorine and bromine and iodine like crazy, because they have 7 electrons in the outer shell. They want 8, so they'll grab an electron anywhere they can get it and become a negatively charged ion. Lithium doesn't do this. It'll lose an electron easily. It will not pick up one easily, because that's just not a stable situation. But they're just doing this for illustrative purposes, showing that's what an ion is. An extra charge, electron charge, or a deficit of electron charges. Okay, so this one is not very realistic. It's also in the book on figure 6.3. Except on 6.3, interesting, that's even worse, really. They're showing helium, and that just isn't how helium lives, okay? I'm sorry. They shouldn't be using these things that really don't make sense, okay? I won't even go there. This one's actually a little better than the one in the book, and they changed from this to that. So, now, anyone ever heard of static electricity?
Yes.
Yeah, of course. Where do you hear from it?
Shock.
Okay, yeah, when you're shocking. When I worked at Southern Research Institution, we were on a radon project and mostly worked down in South Florida, well, Central Florida, around Lakeland and Bartow. Okay, and they did a lot of phosphate mining down there, and that's where the radon came from. Well, when we go down there to do measurements or to do installations or to do, whatever we're doing there, we usually went and stayed at a fairly cheap motel there, somewhere in the Bartow or Lakeland area. And it was always happened that when you scooted along, just walking along on that cheap polyester carpet they had in the thing, and then you reached your door, you would get shocked. Because as you scooted along, maybe rubber soles or polyester, you would build up excess charge. Something was knocking electrons off or picking electrons up. One or the other, that was a net electrostatic charge. It's a stationary charge confined to the object. That's what static electricity means. Stationary, static. Okay? Now, what are those charging mechanisms? One could be friction. I don't know if you've probably seen this illustrated before. Someone take a rubber comb. If you have nice, clean, and fairly dry hair, okay, and comb it, okay, with a rubber comb, and then you might be able to pick up little pieces of paper. Have you ever seen that? That's static electricity. The charge is confined to, usually the electrons, I think, come off your hair and onto the comb. So it becomes negatively charged, and the paper is neutrally charged, but that picks it up because they're unlike charges. stationary, confined to an object. You did that by friction, knocking off the electrons. That's what friction does. Another thing is contact with a charged object. So let's say you have that comb that has become negatively charged. It picked up electrons off your hair, if I had it, whatever. Okay, and you reach down those little pieces of paper. They were neutrally charged, but because the comb is negatively charged, excess electrons, all the electrons in that little piece of paper try to get away from it, because like charges repel each other, unlike charges attract. So the positive charge gets on the edge of the paper near the comb, the negative charge goes there, and when you touch it, now the paper becomes negatively charged because that distributes, and now it picks up the next piece because of the same thing. So contact with a charged object will also be a charging mechanism. And then what I was just mentioning, polarization. It's a neutral piece of paper there, but as you bring the negatively charged comb near it, the positive charges go toward the comb, the negative charges go away from it. Now, even though it's a neutral piece of paper, the charges are not at the same places, so they're polarized. One goes one way, one goes another. Reorientation of the induced is induced without changing the net charge. Okay, that's another way of charging something, either by friction, contact with another charged object, or polarization if you're in close proximity to a charged object. Okay? And here's the gal combing her hair. She thought, well, I'll make my hair look better. It wasn't too bad to begin with. But her hair is neutrally charged. If you count there, 6 positive, 6 negative. The comb is neutrally charged. 6 positive, 6 negative. Everything's happy. She starts combing her hair. And as she combs her hair, the electrons go off her hair onto the comb. The hair becomes positively charged. The comb becomes negatively charged. That's why you pick up little pieces of paper. But what happens to her hair? Her hair is now positively charged. So the hairs try to get as far away from each other as they can. So rather than fixing her hair, she's actually made it worse. Okay? Now, have any of you ever seen a Van de Graaff machine demonstrated?
Yeah.
You have? Okay? Yes. Their hair will take off. I think they're picking up electrons, and as they do, their hair gets further and further apart. Someone just standing there, their hair just picks up and gets the biggest distance it can from each other. And it really is bizarre, especially if you have a woman with very long hair. I mean, it will stand up, she'll be surrounded by her hair. Okay? It's the same thing that happens in the clothes dryer. Hopefully some of you know how to operate a clothes dryer. You don't have mama doing that all the time. But if you pull something out of the clothes dryer, what does it sometimes have? Static clean, static electricity. What has happened is the cottons in there have all been interacting with, say, the polyesters. The cotton will lose electrons, the polyester gain electrons, and now they're opposite charged and they stick together. And some pieces of clothes you actually have to pull apart, and if you listen, they pop, 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 pop as you do it. If you had it in a dark room and pulled them apart, you see little flashes of light as the electrons. That's the same thing, friction, creating a charging mechanism. All right, and then this is the charged comb that had the negative charge from combing your hair. You lean it down little scraps of paper here. As long as you get it close to the paper but don't touch the paper, then the negative charged electrons are going to pull the positive charges this way and chase the negative charges the other way, because like charges repel, unlike charges attract. So what you've done there is polarized the piece of paper. Still electrically neutral, but you pulled the charge centers away from each other. Now, once you touch the comb to the piece of paper, it will lose some of those excess electrons, and this will have excess electrons also, so now it becomes negatively charged. So that's the second one, contact with a charged object. And here we have David here. Okay. Any questions on static electricity and how it happens, why it happens? All right, since more people have come in, let me say this one more time. I may say it again if more people come in. Student course evaluations. They are open. I think they've been open for a few weeks now. If you haven't done them already, do them as soon as you can. Now, if you want to wait to see what your grade's going to look like, you can do that, but please don't forget to do them. It's very important now, so more than most times, because we've got a SACS visit coming up in a few years. They're going to look at the data for several years in the past. We need to have good numbers now. So please do your student course evaluation. That's not the only reason. The other reason is I look at mine to see how students think I'm doing, and I try to adjust my teaching style or activities in teaching. But not just that, I'm a department chair for every full-time and part-time person that is working under me. I use their student course evaluation to evaluate them. Because guess what? The students see them a lot more frequently than I do. So that's what I use a lot to evaluate the staff that's under me. And not just that, on the other side of the house, the administrative side, sometimes those offices don't get feedback like I do from you every day in class. And in lab, we're interacting, so I get an idea of what you're thinking of things. They don't. So the course evaluation is not just for the courses. You're evaluating a variety of things. Please do your student course evaluation and any others they ask you to do. And those of you who've done it, how long did it take? So,
20 seconds. This is tops.
For all your evaluations?
No, per each one.
Yeah, okay. Yeah.
So
usually that people say a little bit more than that, but yeah.
About a couple minutes.
A couple minutes. That sounds reasonable.
They would just keep clicking through.
Yeah.
You gotta be all bad and great with the files.
Well,
Excellent.
you can give whatever you want to give, but please do the evaluations. And by the way, we can't see what you did individually. I will not even be able to see. I guess enough people have done it. I can look now, but all it would tell me is how many people did the evaluations and what my composite score was. I cannot see what anybody gave, and no one can see that. Now, I can see that you haven't done the evaluation, okay? And I can pick that out too. So please do them. Your other instructors can see that too. So if you don't do them and they reward or penalize you if you do or don't, then you might either gain points or lose points for doing it or not doing it. But please do the student course evaluations. No one can see what you put down except you. Okay?
I was Duncan to see because I gave her all X and she didn't like me after
Who's it?
that. Miss Duncan.
Oh,
She didn't
Well, she
like me
could-
before that either. So.
well, okay. I want to say I can understand. Well, I'm not going to say that. Okay, I will not say that. Okay. All right, let's move on to.
I'm at every one of your classes. I'm at your class.
Okay,
I'm at every day.
let's move on to electrical conductors and insulators. Okay. Now, what we've been talking about with static electricity, basically those are insulators because the charges stay confined to one particle. Okay. Conductors, however, charges move very easily. So let's look at the difference. In electrical conductors, the electrons are free to move throughout the material. Okay? If you have a charge that hits a conductor, that charge distributes evenly throughout the whole conductor. If it hits an insulator, it stays at the spot pretty much where it landed. Okay? So electrons are free to move throughout the material. That's what makes them good conductors. Added charge dissipates throughout. Usually, by the way, it gets as far on the surface as it can. But examples of this are metals. And we'll talk about that just briefly. But another one that's a non-metal is graphite. And that's pretty interesting too. that graphite is a form of carbon. Carbon in a two-dimensional array. And if you, let's look at the difference between those two. Your metals are basically in the middle of your table down here. And it says transition elements, okay? And these are mostly your metals. You'll see the blues are your metals. They go all the way to this side and move over that way. Your metals have what they call free electrons. And in the next chapter, chapter 8, we'll be talking about that. Once you get past the first, second, third, into the fourth and fifth shells, energy levels, that's the rows on your column here, then you pick up groups of electrons that are free to move. Like we were talking before, a lithium atom, that one electron in the outer shell, it may be stolen away by somebody else, but then, you know, the electrostatic attraction makes a new compound. In a metal, you have lots of electrons that are free to move freely between the various atoms. In fact, throughout the complex. That's what makes them a good conductor. Now, carbon sitting right here in column 4, it has 4 unpaired electrons. How many does it want to have? 8. Okay? So because it has that unique 4, it can either gain electrons or lose electrons. So that's what makes it a very, but that's only carbon when it's in the graphite form. And we talked about this before, right? That's your dark colored graphite, soot, you know, looking stuff. Now, your electrical insulators. Here the electron motions are restricted. The added charge tends to remain on the object, not distributed through the object, remain on the object. And examples of this are glass, wood in general, diamond, which is also pure carbon. Graphite, pure carbon, diamond, pure carbon. What's the difference here? Diamond is a three-dimensional structure, and all the pairs of electrons are matched up. Graphite, which is sheet, two-dimensional thing, it has electrons that are exposed on the top and bottom edges. That's what makes it a good conductor. Diamond, the electrons are all bound together. It's a really lousy conductor. Okay. But not just that, we have something in between. Semiconductors. Okay? What do you think of when you hear semiconductors? Silicon Valley, right? Okay. The computer industry. And this is a fairly new discovery here. They've known about them for a while, but these either conduct or insulate depending on the circumstances. That could be depending on what kind of charge they have, could be on what kind of type of temperature, or various things like that. The applications of computer chips are all, they're largely built on semiconductors. Solar cells are. Solar cell is sitting there, and when it gets energized, it conducts, and when it's not energized, it's not. And Chris decided he would show up today. That's good. Okay. I know you're in here. There you are. All right. All right. So semiconductors, sometimes are good conductors, sometimes are good insulators. But most of the materials are one or the other without much change. With one exception, okay? And we'll talk about that a little bit later. So let's look again at the electron charge. This will be on page 144. They don't have it entitled the same way they did. This is about page 144 when they say measuring electrical charges. The unit of charge, now this is a macroscopic unit. The microscopic unit of charge is that little electron, okay? That's the smallest unit of charge you can have, a single electron. Sure, a single proton has the same charge, but that's not mobile. That's fixed in place. That electron that can move around, that's your unit of charge. That's called an AMU. Well, no, I'm sorry, that's the atomic mass unit. That's just called the electron charge. That's all it's named. A coulomb is a macroscopic measure of charge. Okay? something you can measure with a device. You will not have any device sensitive enough to measure the charge on an individual electron, ever. Okay? So a coulomb that you can measure is equivalent to the charge of 6.24 times 10 to the 18 electrons. Stated another way, that's 6, 240, 200, 000, 000, 000, 6 of those triplets of zeros following that. I don't even know what the thing. That's beyond trillion, way up there beyond trillion electrons. Okay? This is the metric unit of charge, coulomb. Capital C, why? Again? Named after somebody. I think his first name may have been Charles Coulomb, something like that. But anyway, a French scientist. Now, this is one reason why, when you're talking temperature, you have to put degrees with Celsius, because that's also a capital C, but it'll never be without a degree symbol. If you see a C, capital C without a degree symbol, that means coulomb. Okay, that's the metric unit, SI unit of charge. I would have said SI rather than metric. All right, well then let's think about the electron charge. That's 1/6 quadrillion, 240 bazillion, whatever, of a coulomb. That's the fundamental charge. You cannot get any lower charge than that. Smallest charge seen in nature, the electron charge. The quantity of the charge is related to the number of electrons that are present. Okay, if you have that many, you have 1 coulomb. Okay, and that's usually what we fiddle with, is fairly large, really large numbers of charges. When you comb your hair with that rubber comb, you're exchanging millions of electrons. Okay, believe it or not, just that. Okay, maybe not those of us without much hair, but whatever. All right, so here's the formula that represents that. Q is, by the way, now the quantity of charge. That would be measured in coulombs, macroscopic quantity. Number of electrons, that would be something on the order of this, bigger or smaller. That's your number of electrons times the individual electron charge, tiny little, the smallest amount of charge you can ever find in nature. That's the formula that relates the microscopic to the macroscopic quantity, the number of electrons. Make sense? Oh, I could have left it up there because this is following me. So, if you wanted to find out how much the electron charge was, divide it by the number of neutrons. Number of electrons. So then the single electron charge would be, let's say that's 1 coulomb, divided by how many electrons make up that 1 coulomb, 6.24 times 10 to the 18. When you divide that out, especially if you use a calculator to do it, you'll find that's 1.60 times 10 to the minus 19 coulombs per electron charge. That would be 0.000000000000001 6. Okay. It's an incredibly small number of coulombs to make 1 electron charge. Okay? Those are just reciprocals of each other. Easier way to do it, if you have a reciprocal key on your calculator, type in this one, hit the 1 over x key, or x to the minus 1 key, and you'll get this one. Okay? Now, for those of you who do have the new books, the physical constant, front inside cover of your text, if you look down there, second column, the right-hand column, it says goodness gracious, where is it? Oh, there it is. Fundamental charge, 1.60 times 10 to the minus 19 coulombs. That's for each electron. All right. And that is called the fundamental charge, the charge of an electron. So let's see. Let's do example 1, 6.1. Combing your hair, okay. Now this is why sometimes you won't see it working. On a day with low humidity. We live in the southeast. We don't really have too many days with low humidity. This time of year you'll be more likely to because it's a little bit drier. But especially if you're inside where you've been heating the air, dropping the humidity, okay? So you're combing your hair, and your hair needs to be sort of clean too. If you haven't washed your hair in a few days or something, and it's oily, you're not going to see this happen. The oil keeps the electrons from transferring. So it needs to be relatively clean and relatively dry. Not just your hair dry, but the room, the humidity in the air is low. Results in a comb with a negative charge on the order of 1 times 10 to the minus 8 coulombs. Let me get my pen set up. Okay. Nope. There we go. So the charge, what's the symbol for charge in this chapter?
Capital C.
Q.
Okay, capital C is the unit for charge. Q is a symbol for charge. Q, okay. Now in the last chapter, Q was heat, remember? Okay, don't get the two crossed up. They have so many things we're representing, and the electric people don't talk with the temperature people, and they use the same symbol. But Q in this chapter is charge. That charge, they told you here, is 1.00 times 10 to the minus 8 coulombs, capital C coulomb. Okay? How many electrons were transferred from your hair to that comb to give you that little amount of charge? I mean, that's a small amount of charge. That's 0.0000001, or something like that. Just a very small amount of charge. That's why you don't really feel any click with it, but you might feel just a little bit. You'll see your hair stand up. So how many electrons were transferred for that tiny, and by the way, 10 to the minus 3 would be millicoulombs. 10 to the minus 6 would be microcoulombs. This would be 1/100 of a microcoulomb. I mean, you're talking a very small amount of charge. How many electrons were transferred from your hair to the comb? So we're looking for N, the number of electrons, right? Okay. Well, we know what the electron charge is. It was just on the screen. Remember what it was? 1 point. Remember it? 60 times 10 to the negative 19 electrons. Okay, I'm sorry, coulombs per electron. Sorry. Coulombs per electron. That's the fundamental charge. Coulombs per electron. My symbol for electron is E with a minus by it. Okay? So, if you're looking for N, what was that formula that related Q, N, and E? Do you remember it? Remember that formula? Q is equal to NE. Okay, we're looking for N, so we're going to divide both sides by E, right? Or you could do your little triangle or circle or something like that. This will give it to you. N is equal to Q, which was 1.00 times 10 to the minus 8 coulombs, divided by E, which is 1.60 times 10 to the minus 19 coulombs. Is pretty exciting stuff, huh? Coulombs per electron. Okay? And notice here the coulombs will cancel out, and you're going to be left with number of electrons. 1 over E would be E's. So if someone has a calculator that does scientific notation, and you know how to do it, punch this in. Anyone got a calculator that will do it? Guess what, folks? You might need one on your next test, so I would locate a calculator, learn how to use it. Any of you got one? Nobody? Okay. You know how to use scientific notation on it? Let's see yours. Here's the key with times 10 to the x, okay? That's your scientific notation key. Most calculators have either an EE key or an EXP key. You actually have one that's times 10 to the x. That's what you want to do. So what you're going to punch in, that's to multiply it, is 1, okay? That times 10. And then on the next thing you're going to do to the minus 8, did you punch that in? Okay. Now, what he shows here is 1.00 times 10, that's the thing. And then it's ready to enter something up here. Now, if you have a scientific calculator or better that has one of these minus signs in parentheses, that's your negation key. This is your subtraction key over here. Don't use that. That's going to try to subtract whatever you enter next from this number here. That's not the one. You want this one, which is going to, and when you enter that, you see you get a little minus sign up there, right? Now press 8. Okay. Now, tell me what happens when you hit the division key. Second? Yeah, then that's exactly what you hold. Not using your calculator. I guess that's okay. Okay, we'll see if the numbers come out right. Okay, divided by, this time put 1.60 times 10, your times 10 key, and then put the negative in parentheses, 19, and then press enter.
6.25 times 10 to the 10th.
Okay, what'd you say? 6.25
times 10
to the 25th power?
10.
Okay, that's number of electrons. Let's see how they did.
10 to the 10th.
10 to the 10th, that's what I was going to say. 25 is too many. 10 to the 10th. Okay. Okay. That would be 62.5 trillion electrons to get that little amount of charge.
What did you do?
62.5 trillion electrons to get that little amount of charge. That shows from the microscopic to macroscopic. And a coulomb isn't a lot of charge, and certainly a hundredth of a microcoulomb is a very small amount of charge, but it still took 62.5 trillion electrons to get that little amount of charge. So yeah, so you punched them in right. Those exponents were looking awfully big. That's what I was worried about. All right, so let's move on to any questions on electric charge. Okay. Let's move on to electrostatic forces. We've already talked about that. We're going back to static. We just about got to moving charges in conductors, but we didn't quite get there. We're still talking about electrostatic forces. And these follow Coulomb's law. Okay? It's the relationship giving the force between two charges. So let's say we have a charge out here and another charge here. Okay? This can be so many coulombs or whatever. The form of this equation is very similar to Newton's law of gravitation. I don't know if you remember that, but I think they're going to show you both of those here. Let's see. here is Coulomb's law. The electrostatic force, F, what do we measure force in? What units? Newton, exactly. Okay, named after Sir Isaac. So this is K, which is a constant. This is one of those proportionality constants, because the force is directly proportional to the product of the charges, inversely proportional to the square of the distance between those charges, and that gives you your force. So this proportionality constant is a dimension quantity. It has to have newtons in it because there's no newtons here, so this has to contain the newton, okay? Meter squared because the distance is in meters, okay? Per coulomb squared because each of these charges are in coulombs. So that's why you get K to be 9.00 times 10 to the 9th Newton meter squared per coulomb squared. Because when you multiply by coulomb squared, that goes out, multiply by meter squared, that goes out, and you're left with newtons. Okay? That's a big number. That's 9 trillion, okay, newtons meter squared per second squared. Huge number. Okay? That's your K. Now, how does that compare to G, which was our universal gravitational constant? I don't know if they're going to give you the formula. I can't see it on this one. Let me go on and give you, to remind you, this was F sub C for coulombs. This is F sub G for the gravitational force. Okay? That was capital G times the product of the masses divided by the distance between them. So it's almost the same form. It's just that G is your proportionality constant for that one, and that will be in Newton meter squared per kilogram squared, not per coulomb squared. A kilogram is a huge unit, and a coulomb is a little bit smaller unit, so you're dividing by, multiplying by that. So this is going to be a smaller number, but look how much smaller. The G, oh, there it is. They did give it. I forgot whether they did or not. Okay? So compare, you see the formulas? There is Coulomb's law, F is equal to K, Q1, Q2 divided by D squared, whereas gravitational is F, I wish they'd put the G out front like they did the K, G, M1, M2 divided by D squared. This G here is 6.67 times 10 to the negative 11 Newton. And here they made a misprint. That should be, it's 2 misprints, okay? It's Newton meter squared per, oh, no, I'm sorry. They got it right. I wasn't paying attention. I don't know if you've had this in math before. I think you should have. That when you have a negative exponent, that moves it downstairs. So this is the same as Newton meter squared per kilogram squared, or times kilogram to the minus 2. So they got it right. Okay. Whereas, look at the Coulomb's constant. It was 9.00 times 10 to the positive 9 Newton meter squared per coulomb squared. See, I wish they'd have done them the same way. This would have been Newton meter squared and then put it over a kilogram squared. That would have made it look more similar. Okay. So, guess what? Electrostatic forces are much stronger than gravitational forces. That's why those little pieces of paper, when you've combed your hair, put the comb near it, you can pick up the paper and have a string of them there. Because the electrostatic pressure, forces are stronger than gravity, which is trying to pull them down. So, except electrostatic forces have a very small range of influence, where gravitational forces, even though they're weaker forces, they travel millions of miles. Okay, so yeah, you got a lot of differences there. All right, any questions on that? Electrostatic forces. Okay. Oh, and here's the comparison of the two. Okay. I'll go and take off that 2 that's sitting there. Okay. K was 9.00 times 10 to the 9th newtons meter squared per coulomb squared. G was 6.67 times 10 to the minus 11 newton meter squared per kilogram squared. Okay. Now part of that is because kilograms are big and coulombs are small. Still not that much. You look at the ratio of those two, you can punch this in on your calculator, you'll see that's 1.4 times 10 to the 20. Now that's not really a fair measure because the units aren't the same. The numerator units are the same, but the denominator units are very different. Still, it's a big change in magnitude, huge change in magnitude. All right. Before we get to force fields, let's do example 2. Electrons carry a negative electric charge, we've already said that, and revolve around the nucleus of an atom. Okay, we've already talked about that, which carries a positive charge. Now you might say, why don't they crash into the nucleus? Because the nucleus is positive, they're negative, why don't they attract and go in? Same reason, gravitationally, that we don't crash into the sun. We're always falling to the sun, but because we're in a orbit around the sun, we have a velocity in this direction, the attraction this way, so that just keeps changing our direction. But we're always falling toward the sun. It's just that our velocity keeps us from crashing into it. Okay? Hopefully it will always keep us from crashing into it. Same thing true of the electrons. They have a lateral velocity, which is quite fast, and it keeps them revolving around the nucleus, not crashing into it. Okay? So, electrons carry a negative charge, revolve around the nucleus of the atom, which carries a positive electric charge from the proton. The electron is held in orbit by the force of electrical attraction at a typical distance of, so your D down here, or that we had before, D is equal to 1.00 times 10 to the minus 10 meters. Okay? That is a very small number. That would be 10 nanometers. Okay? Because nano means 10 to the minus 9. So anytime you hear people talk about nano, if they're really using the term properly, you're talking about atomic distances. Really, really, really small measure. So that's your D. What we're looking for, what is the force of electrical attraction between the electron and the proton? Well, what was our formula for electrostatic force? Anyone remember? Worth remembering. Had it on the previous slide or so. K, which is Coulomb's constant, right there we have it. It's on this slide. That's the prompt. Say again? Okay, capital C was the unit, but it's Q1, Q2. That's the parameter for it, divided by D squared. That's it. Okay, so we're talking electrons and protons, which have the fundamental charge. So this will be 9.00 times 10 to the 9th. Remember the units for that? Newton meter squared per coulomb squared. Okay? That's your K, multiplied by your fundamental charge. Remember that one? 1.60 times 10 to the minus 19 coulombs. That's for a proton. It's also the same for an electron, so you square that. Divided by the D up here, 1.00 times 10 to the minus 10 meters squared. Okay, because you're squaring the distance, D squared. So someone got a calculator? Or to give it away, you do. Okay. Anyone who has one, it's a good idea to get used to being able to input these formulas because you may be needing to calculate them. Okay? 9, your times 10 key, 9, times 1.60 times 10 key, and then your negative in parentheses, 19. Okay? Now that number is squared. Now I'm going to have to see how your calculator does it. Do you have a square key? Do you see that on there?
Yeah, I think I have to put it in parentheses.
You might do. That's why I said I'll have to see how the numbers turn out. I think the square, well, okay, divided by 1 times 10 key, your negative in parentheses 10, but that's also squared. Get an equal key and see what you get. You get a number?
2.304.
2.30. Don't give me any more digits because this has 3, that has 3, that has 3, that has 3. All of them have 3, so stop at the third one. Times 10 to the, what do you say?
8.
-8 newtons. Okay? That's not a huge force, but it is when you think of how tiny these things are. It's a pretty significant force. And that's exactly what the book got. All right, does that make sense? Okay. Now let's move to force fields, the next subtopic on page 145. How do forces act through space? We're really not sure, but they do. Gravity acts through space, electric fields act through space. Charges are surrounded with electric fields. Those are things that they have no mass, they transmit forces. They are vector fields, meaning they are directional. Remember, these fields are either pulling things together if they're oppositely charged, pushing them apart if they're similarly charged. They always are vectors. The fields and the charges are inseparable. If you have a charge here, it has a field around it. Fields act on other charges. Now, if that charge is isolated there's a field around it, but there's no other charge for it to act on. But if you bring this other charge here, okay, now it's going to sense that field. It'll either be attracted to it or repelled from it, depending on the nature of the charge. Okay? Now, if they're far enough away, they don't notice each other. But if they're close enough, they definitely do. So fields act on other charges. The direction of the field is the motion of the positive test charge would move if it were in the field. So here's a charge up here. You tell me, is that positive or negative? Tell me. Make it up. Positive. Okay. Now, if you brought a small positive test charge close to that, where would it be? What would it tend to do?
Go away.
Go away, exactly. So the fields are pointing away from a positive charge. Always. If that was a negative charge up here, and you brought a small test charge, positive test charge in here, what would it be doing? Attracted. So the field lines are always going toward a negative charge, away from positive charges. Okay? So the direction of the field or the motion that a positive test charge, if you put it there, would have. Visualize with these lines of force. We're going to show one in a second. The same ideas apply to gravity and magnetism, with one exception. What's different about gravity? What's different about gravity? We said the same idea applies to gravity and magnetism. What's different about gravity? It never repels, always attractive. Magnetism can be repellent or attractive, either one. Gravity is always attractive, unless you find something with a negative mass. Okay, never mind, you don't. Okay, so here's how we do it. If you have a negative charge here, and that negative charge, and you were to bring a small positive test charge in here, it's going to be attracted to it. So the field lines are always pointing toward negative charges. Whereas if you had a positive charge there, brought a test charge here, it's going to tend to push it away. So the field lines are always pointing away from a positive charge. Always. Field lines point away from positive charges toward negative charges. Okay. Nothing there. Okay. Okay. There's some things that should be showing up that are not showing up. Okay, here we have something. Let's see if going backwards. Nope. All right. I hit the button a couple of times. Nothing showed up. If you have your books on page 146, top of the right-hand column, it shows two opposite charges, one positive, one negative, showing these force lines, field lines, going toward each other. This is showing two positive charges. Well, the positive charges, which way does the field lines go? Away. Okay? So these are pointing away, these are pointing away. These field lines can never cross. They can connect, but they can't cross, but because they're both pointing away, that bends the lines away, pushing them away, sort of like springs here, pushing them away. That's why they repel each other. Okay? Now, if we had had the, let's see if it's showing, oh, here it is. They just got them out of order. Okay? This is a positive charge, and that's a negative charge. What field lines are on a positive charge? What direction are the fields? Away from a positive charge, and how about negative charges? Toward the negative charges. So you see these field lines are pointing away, and they're going right toward the negative charge because the field lines go toward that. So that's why they're attracted. They're pulling them together, not pushing them apart. Now, let's go back to the previous one. Okay? If you can imagine this, I can't do it well because the shadow's too much. If you could imagine this, get closer and closer here, a little circle around there, you almost have even distribution of charges. But the further out you get, you see, the more you see their bent. Okay? Whereas on this one, it's pretty easy to see. You know, you turn around here, that looks like just an isolated charge. That looks like an isolated charge, but the field lines are connecting, and therefore they come toward each other. They never cross. They can connect, but they never cross. They only connect if the arrows are pointing in the same direction. Okay. Does that make sense? This is just a visualization of it. There's really no lines there. You can't feel them, but they act as if they're lines there connecting. Okay. That was field lines, force fields. Now we're moving toward the concept of electric potentials. Finally, something we can sort of measure. Okay? What device do we use to measure electric potential? Anyone know? A voltmeter. Okay? Because, well, close anyway. Electric potential is a scalar field. Now, I really don't care for calling it a field, but I guess it's okay. Associated with the potential energy. The unit for potential, electrical potential, is the volt. Now, here is sort of a problem, folks. It's not a problem, it's just an occurrence. Chelsea's here, that's an occurrence too. Okay. We're slowly getting everybody back from Thanksgiving. Okay. The symbol that represents charge was what? The symbol.
Q.
Q. The unit was C, capital C for Coulomb. What's the symbol that represents voltage?
V.
V. What's the unit for a volt? For voltage? V for volts. Okay. They use the same, almost the same nomenclature. Okay. And it's capital V. Why do you reckon they're capital V?
Because it's named after someone.
Named after Volta, okay? Alessandro Volta, okay? He was an Italian physicist. A little bit on the history of charges and things like this. Actually, the first person to discover electric charges per se was not a physicist. He was an anatomist.
Really?
Yes. He was studying frogs, dead frogs, soaked in formaldehyde, and he was using his little tweezers to try to separate the muscles and to locate the nerves and that kind of stuff. Really fine work there. And it happened to be that he had his tweezers, I don't know, let's say they were copper, okay? But his probe, let's just imagine it was iron, okay? The deal is it was two dissimilar metals, okay? And as he was doing, he was holding this with the tweezers and touched this. Now, it was a dead frog, okay? A dead frog, been soaked in formaldehyde for weeks, maybe months. I don't know how long.
Maybe years.
Maybe years, okay? He cut off the leg off the dead frog and was analyzing it, okay? And when he held it with his tweezers and probed it with his iron probe, it twitched, okay? He had to empty his drawer. He was really surprised because he thought he had just discovered life. This was a dead frog. The leg had been cut off the dead frog, and yet he got it to move. He said, have I just found the source of life? Okay? He was really pretty excited. Okay? So he started fiddling around and trying. Ultimately discovered, no, it wasn't. It was just some freak of physics. Nothing to do with life and anatomy and stuff. So he wrote it up and reported it, told about it. And his name, by the way, was goodness gracious, Galvani. And actually we named a cell, galvanic cell, after him. Even though he was an anatomist, we still named the physical thing after him, galvanic cell. Because he first discovered it. But this other Italian, Alessandro Volta, happened to live at Lake Como, Italy. I don't know if you know where that is. It's really up in very northernmost part of Italy, right next to Switzerland. Okay, very, very close to Switzerland. The only reason I know all that is that my wife had professional meetings one time in Lake Como, Italy. And it was right in between terms when I had the week off. I got to go with her. Okay, her niece got to go with us too. And while Karen was busy in meetings, her niece and I were roaming around Lake Como, traveling the tram, going over to Switzerland, buying chocolate, doing all sorts of fun things. But while we were walking around, we saw this really elegant-looking structure out there by the lake. So we went over to see what it was, and it was a memorial to Alessandro Volta. And in there were some of his first cells that he put together. He put together the first batteries out of dissimilar metals with electrolyte in between. With the frog leg, the formaldehyde was the electrolyte, okay? And that's why he was able to get it, Galvani was able to get it to twitch, okay? Didn't mean to, but he did, because he had dissimilar metals. And they had to be conductors too. All right, so anyway, that's who Volta was named after. Volt was named after Alessandro Volta. Related to the work involved with positioning charges, okay? So let's say we have that charge here. Which did y'all want it to be? Negative, was it? Positive. Well, this is a positive charge here. And if you're trying to bring in another charge and place it somewhere, if this is what you want this to be, positive or negative? You choose.
Negative.
Negative. If you're trying to bring this in to place it somewhere close to that other one, you're going to have to hold it back because it's trying to go toward that positive charge. But if you're bringing in a positive charge, you have to do positive work to force it there, okay? So that's what a volt is measuring. It's related to the work involved with putting charges, either like charges or unlike charges, in the proximity of another charge. What we call that is the potential difference. That's what's important, in producing the forces and moving charges. The potential difference, that's what your volts measure. Not potential itself, but the potential difference. It's analogous to moving masses in a gravitational field, except in a gravitational field, it's always attractive. So you're always having to hold them back, the work to keep them from crashing into each other. Okay. So here's the example. Here's your fixed charge, 1 coulomb, positive, just like you have. And I'm trying to bring in 1 coulomb charge, and I'm going to do 1 joule of work to bring it in. I can move that 1 coulomb charge 1 meter toward that other one. That is a joule per coulomb. That's what a volt is. Good thing to remember. A volt is energy, joule, potential energy joules per charge. Coulomb, joules per coulomb. That's what a volt is. Okay. So here we have it. Now again, the symbol, the parameter for voltage is capital V. The parameter for work is capital W, because little w is weight. So this is capital W here. Charge is Q. So potential, electric potential difference, is work per unit charge. Joules per coulomb. Joules per coulomb, the units, that will also be capital V, the volts, because V, capital V, is both the parameter and the unit. Sorry about that. I kind of screwed up there. All right. So let's now look at electric current. Earlier we were talking about electrostatics, and we were using Coulomb's law, remember? And K was Coulomb's constant. You can always find that in the front of your book if you have one of the new books. There, Coulomb's law constant, K is equal to 9.00 times 10 to the 9 Newton meter squared per Coulomb squared. Okay? That was electrostatics. The charges are more or less fixed in place, and you're just measuring the forces between them. But with electric current, the charges are free to move. You've got conductors there that allow them to move easily and freely, almost freely. Okay? The electric current is the flow of charge. Okay? Now, this is a little bit better than flow of energy. Energy, there's really nothing to move. Flow of charge, there really are charged particles that do move. But that's really not what's doing most of the motion. We'll talk about it later. The reason for the charge flow is the potential difference, the voltage between the objects. If this is at a +7, and that's at a -3, you have 10 volt potential difference between the two, and the charges are going to be moving from, and there's another problem. We'll get to that later. All right, so what is an electric circuit? That's a structure, I like to use the term pathway, designed to localize and I don't like to use currents, okay? Electric circuit uses that electric current, localizes and uses those electric currents. Typically, we almost use these two words interchangeably, but they're really not quite, okay? The circuit is the physical structure, the current is the energy moving. All right. So what's that structure like? The circuit? You have to have a voltage source. If you don't have a voltage source, you don't have a current. Okay? You've got to have a voltage source. That is your energy input. If you don't have any energy input, nothing's going to move. It can't. Okay? It's necessary for continuing flow. Now, there's one exception to that, and we'll talk about that a little bit later. But hang on to the concept. You don't always have to have a voltage source, but that's a very, very special condition. We'll get to that later. Now, you also need some circuit elements. If all you have was potential difference, yeah, charges would move, but there's nothing to use that energy. So basically, your wire's going to heat up and probably burn out. Okay? So you need something to use the energy, and that could be a heater. It could be a light. It could be electric motor. It's something that uses the energy that the voltage source is providing. Now, one thing they didn't mention here, and they need to, you have to have the pathway. Because if you're not connected, even though you have a device here that can use the current, you have the voltage, use the energy, and you have the device here, a voltage source that provide the energy. If you don't have them connected, nothing's going to happen. Nothing will happen. You have to have the pathway. Okay? Now, here's where we get into problems. And I've heard that it's basically Benjamin Franklin's fault. Now, I don't know if that's all his fault or not, but it was just an arbitrary decision, and some people have suggested he's the one that came up with it. We know there's two charges, positive charges on protons, negative charges on electrons. But you know, before, when they just knew there were two charges, no one knew what was positive and what was negative. And they say that Benjamin Franklin said, well, let's just make the positive charge in the nucleus and that little electron flying around there, the negative charge. Well, that created a little problem for us. Because here's your voltage. Okay? Now, they're not showing here in this picture the two poles. You see the two poles, but you can't tell any difference. In your car battery, which that looks like, right? What's the difference between these? Say again? Negative and positive. Usually the negative is red, and which is positive is red, and the negative is black. Okay? And that's usually the way we think of it. Says positive is positive and negative is negative. Positive is a higher potential than the negative, right? Now, in everything else in physics, things move from high potential to low potential. Remember our heat engines? From high energy to low energy. Temperature, from hot objects to cold objects. Everything moves from high potential to low potential. Always. Except with the current. Okay? If this is your positive pole, that's your negative pole, then this would be what we call our conventional current. Okay? The current flow convention is from high potential to low potential through the external circuit. So if this is your conventional current, this is your plus, there's your minus. It flows from plus through the light, back to the minus, and then back to the battery. Okay? Now what's in the battery? Anyone know? Second? Cells, okay? Typically this has 6 cells in it, doesn't it? Yeah. Okay? And those cells are made up of your lead storage batteries, lead sulfate, lead sulfate, lead sulfate. Okay? And in between that is acid, sulfuric acid. Now, some of the more modern batteries may have different materials and stuff, but they basically are the same type thing. And with that going on, that provides the energy as it moves through the battery. That provides the energy goes through, is expended here, comes back here, gets energized again, goes again, just keeps it going continuously. Okay? The work is done there. But if we were talking about electron, and I'm jumping ahead, so let's follow the book. Okay? Here is what they call the water pump analogy. Here we have a pump. What does the pump do? It brings Ashlyn into the room. Okay, very good. All right.
I don't think that's what the pump does.
What does the pump do?
I don't think that's what it does.
What?
I don't think that's what it does.
What? Bring Ashlyn into the
Yeah, I
room?
think it does.
If you had an Ashlyn pump out there, okay. All right. All right. So this is a water pump. It wouldn't be bringing it in unless you was surfing or something. Okay. What the pump does is raise the potential energy of the water. It picks it up and pumps it up here, right? So you give an energy to water, gravitational potential energy, by pumping it up, right? Well, to pump you up, you don't remember. Okay, never mind. Okay? Then the water comes out of the upper tank and falls on the paddle wheel, the water wheel here, and that turns it, and that could be a generator or something, right? That's using the energy the pump gave it. Okay? Now, let's put our circuit elements in there, and you tell me what corresponds to what. And by the way, since we're about to lose somebody, let me say this again. I can't remember if I said it when you came in. If you haven't already done your student course evaluations, please do them. They're really, really pushing on this now. So please don't forget to do your student course evaluations. All right. You know what we're going to do next, Chris? We're going to the lab and have a 2-hour lab. Then we're coming back here probably and have a 30-minute test. So whenever you get back, will be one or the other. Right now, the equipment is in 252 because somebody was in 253. If we can use 253, we'll be there. Otherwise, we'll be in 252 across the hall. So what would be analogous here to your circuit? What's analogous to the voltage source in your water pump analogy? Anybody? What's analogous to your voltage source here in your water pump analogy?
The moving of the water.
Okay, that would be the current.
Okay.
The current would be the moving water. What would be analogous to the voltage source? Okay.
RPM.
The wheel would be equivalent to, say, the light bulb. That's what's using the energy. What would be analogous to the pump?
Pump would be the battery.
The battery. The voltage source is what's giving the energy to, and what would be equivalent to the water?
Wires. Or the current flow.
The current flow, exactly. So there you have it. Okay? Now, here's a place, all analogies will break down somewhere. And here's where this one does. What if you cut this line right here, going from the pump to the thing, what would happen?
Stop the flow.
Water would spill out everywhere, right? Because there'd still be water being picked up here. If you do it to the wire, though, by the way, this is the wire. The pipe is the wire. Yeah, if you break this thing, everything stops. The pump doesn't continue working. The battery doesn't continue pumping unless you have a complete circuit. So that's sort of where that falls apart. Okay? Okay. Now we're moving on to the nature of current. And this is what I was starting to say before, and I had to shut myself up. All right. Now this is showing it different from the last one. Okay? The last one was talking about, I'll show it to you. It said the current flow convention, yeah, that was the picture. Okay. Current flow convention is from high potential to low potential. So if this were doing what it said there, that would be the plus terminal, the minus terminal, and the current flow goes like this. However, this picture shows it the other way. This shows the plus here, the minus there, because this is showing the movement of the charges. The electron current is flowing in that direction, but the conventional current is flowing from high potential to low potential. So they flipped around their illustration here, but now the conventional current is going this way from high potential to low potential, which is what it was before, but the arrows here are showing electron current. Okay. And that's all Benjamin Franklin's fault. Since he chose to have electrons being negative, then that sort of screwed up our conventional currents going in the wrong direction for electron current. But it really is the right direction because electrons are negatively charged, not positive or neutral, so they would go in the opposite direction. Okay, enough of that. All right, so historically, the nature of the electric fluid was unknown. We didn't know what it was. Current thought is to be the flow of positive charge for conventional current. But what are positive charges? What part of the atom?
Proton.
Protons. Do protons float around and move?
Yes.
No, because they're fixed in the nucleus. They don't move
I
around.
mean, I guess.
It has to be a nuclear reaction to make them move.
The nucleus moves.
It may move some, yes, but generally it's the electrons doing the moving because they are such lightweight, almost massless. Okay. So the current is thought to be the flow of positive charge, which is usually not good. Now you're absolutely right. Inside your battery, you've got positive charges, ions moving in that direction, and negative ions moving in this direction. So you do have, they're not really atoms, they're ions moving in opposite directions. That's what the battery does. Okay, that's what gives it the energy. Okay, so in reality, it's a lot more complicated depending on the material. And let me give you a hint. We're going to talk about it later too. It's not really the electrons. The electrons do tend to move in that direction, but it's not like you get an electron here and it races through here, it goes through there, and races back here. It doesn't. Those electrons move incredibly slowly. Incredibly slowly. So it really goes back to our fields. The fields are what move instantaneously, not the electrons. Okay? Now, reality is more complicated depending on material. The opposite is correct in metals. The current is, in a sense, an electron flow, but that's only in a small sense. Really, it's a field phenomenon, not really a movement of charge that much. The charges do move. Because what are your charges doing in an AC circuit? This is all DC.
Okay.
Yeah, they basically are going nowhere. They're just going back and forth, back and forth. Okay, they're not going through the light at all. They're just going back and forth, back and forth. It's the field that is creating and transmitting the energy. All right. So here are the current mechanisms. This is basically the nature of current. No. Yeah, it's under the nature of current, but it's on about page 150. Okay. So what we have here, let's deal with liquids and gases first. And sort of what John was saying was right. Here we do have positive and negative charges moving, not protons moving, but positive ions and negative ions moving, just like you have in the battery, okay? Just like you had in the frog legs, okay? Both were moving, positive and negative charges in the form of ionic charges, okay? In metals, though, it's the electrons moving. Those electrons, they're delocalized, they're not belong to this atom rather than that atom or that atom. They're shared among all the atoms, okay? So they're delocalized electrons, free to move throughout the metal and form sort of what some people consider an electron gas. But here's the deal, folks. That drift velocity of those electrons is incredibly slow. Incredibly slow. I think there'll be an example coming up at the top of the next page. Because here's what's happening with those electrons. Okay, what you do is impose, okay, this one has no field imposed. Now this isn't quite accurate. You should have these randomly distributed, not negatives here, positives there, negatives here, positives there. Very randomly distributed, but they did them there for illustrative purposes. You put an electric field, impose an electric field in that direction. Now what does that tell you? That would be the direction that a small positive charge would move, that way, okay? So that means your electrons are going to try to move this way because they're negatively charged. So this electron picks up and happens to be attracted toward that positive charge, and then it's attracted toward that one and that one and that one. Now this is idealized. In reality, that electron's coming here, it might bump into another electron and bounce back, but then still is pulled that way and then maybe hit another electron, bounce back over here. So here's the direction it's going. It's just going all over the place, but generally slowly drifting in the direction you would expect it to go. It is a very slow process. The electric field moves at nearly the speed of light. The electron itself, incredibly slowly. So therefore, when you hit the light switch and the light comes on, that's not because the electrons raced up there and went through the filament of the light. No, the field did that. It was the electrons right next to there, they moved. Not the ones from the switch. They all moved at once because the field was set up throughout. Okay? Let's see if this example is given. It's not on here, so I'm going to, I'll do it here. It's not an example exactly, but it's an automobile. Okay? Y'all are familiar with those? Okay. Now, what kind of current do you have in an automobile?
DC.
DC almost exclusively, right? So, say again?
Thank you, Adam.
Very good. Okay? Now, let's say that your battery is in the front of the vehicle. Not all vehicles are like that, but most of them, the older ones are. And your taillight, okay, here at the back of the vehicle. And that's about, this estimates 2 meters apart. A little over 6 feet apart, right? Close?
What is?
The battery to the taillight.
Probably.
Okay.
In some vehicles.
Okay. So, let's say you pull the switch to turn on the lights. Come on pretty immediately, don't they?
Yes.
Well, let's say we were tracking an electron from the battery to the taillight. How long would that take?
Pretty much the speed of light.
No.
No?
The field is the speed of light. That electron drift velocity is about 1/100th of a centimeter per second. That's 1/10 of a millimeter per second. That would be, if I have a dime on me, I don't, let me use a penny. The thickness of that penny, divide that penny into 10 equal sheets, okay? Pretty small. That's how far it would go in a second. The thickness of one of those little sheets. At 1/10 of a 100th of a centimeter per second, 1/10 of a millimeter per second, the distance of 2 meters, which would be 200 centimeters, the time would be more than 5 hours, 5.6 hours to go from the battery to the taillight. It would be light by then. You wouldn't need your lights on. No, I'm just kidding. Okay. It's the field that travels almost at the speed of light. The electrons do not at all. All right. Now, there's a little blurb at the top of page 151, and this is myths, mistakes, and misunderstandings. What is electricity? Okay? Okay. I was just looking at, there's a part of me that feels like I've done the wrong lab first, but I think we're still okay. I'm not going to read that to you. I'd suggest you read it yourself, but it's a pretty interesting little thing. It's not just a movement of electrons. It's an imposition of the field. All right. How are we doing?
It is
Not-
5:10.
Not too much more. Let's see what we can get done here. Okay, there was our water pump analogy. Nature of current, we've already talked about that. Here we go. Here we talked about the nature of current mechanisms. Let's now talk about more current details. Here is the formula that describes what current is. Okay, I represents current. Now, for some reason, it's usually always a capital I. Has nothing to do with being named after anybody because it doesn't really have a name. That's the parameter. The symbol for current is capital I. The symbol for, what does Q represent? I'll ask it the other way, but not this way. What does Q represent? charge. And T represents time. So current is charge. It's the charge flow. The time rate of change of current. Of charge. That's what current is. Remember from the very beginning, anytime we came up with something, let's do a time rate of change of it, see what we get there. Distance, time rate of change of distance is speed. Time rate of change of displacement is velocity. Time rate of change of velocity is acceleration. Time rate of change of momentum is force. Time rate of change of energy is power. Anytime you get something, divide it by time, see what you get there. We'll start with charge. Time rate of change of charge, that's what current is. The flow of charge. How much charge is flowing in a given time. Okay? So the current is charge per unit time. The units are amperes or amps. Why capitalize? Why capitalize? Named after Louis Ampere, another French. Now, if you notice, a lot of electricity seemed to come, a little bit from the early Italians, and then it seemed to center in France. Well, about the time this was happening, France was at the peak of its, France has had several peaks. Charlemagne was the real peak. That was way back, way back in time. But this was around Louis the 14th, 15th, 16th, 16th was the one that lost his head, but the ones before him, the French, it wasn't really an empire, but the country of France was at its peak. They were the center of lots of things, art, science, music, lots of things. That was France's big time in modern history, you might say. And so therefore, a lot of the leading scientists, they could afford to support the science, and that's for electricity that happened to be happening just around that time. So named after Louis Ampere. Now, direct current is when the charges all move in one direction. Okay? Now, they do like this as they're moving, but the trend is in one direction. Most of your electronic devices, your calculators, your computers, everything like that is DC. Anytime you have any kind of a box like this in between your plug and your device, that means it's DC. Now, it doesn't have to be a big box like this. It could be a big plug like that. That's changing the AC to DC. Your electronic devices are DC. Okay? Batteries, solar cells, all those are DC. That's one of the little problems with solar energy. Solar energy from a solar cell, DC, but we all use and transmit AC. So they have to, the power company has to be able to convert that and change it. And you have some loss of energy, inefficiency by doing that. But that's what we get. Alternating current, on the other hand, is the charge motion is oscillatory. It's not, there's no net current flow at all. It's just the charges are moving back and forth, very, very, very rapidly, so they're not going very far, but they're all moving in the circuit like that, and that motion is what carries the energy. Okay? Not that the charges are going through and making something happen. So that sort of indicates it's not really the flow of charge. It's the energy the charges are carrying. So there's the definition for current. Now, I think we're at a stopping point, and this will be where we'll end today, electrical resistance. Right? Okay. And I think all of you probably know what's coming with that.
Break.
Say again?
A break.
A break. Well, yeah, we're going to break and go to lab. Before you do that, let me go on and pass out the lab. Let me end this slideshow. Wait, that's not what I want to do. Yeah, don't do that. Okay. All right. A few people have come in since I said this. Today we're doing lab now for 2 hours, and then we're going to have the test on chapter 4. Okay? This lab is on chapter 6. the one we're currently in. So I'm also going to pause my reading. All right, now we're recording. I want to get back. Okay, read the first paragraph or so. Talk about the circuit, current, flow of charge, that kind of stuff. End of the procedure. Now we're not got a battery, a flashlight bulb, one battery, and one piece of 10 centimeter piece of hookup wire. We're not doing that. Okay. What we are doing, if you'll turn to, instead of that, if you'll turn to page 180, okay? Now you see there, okay? Notice the rectangle with the dotted lines around it. Completely blank, right?
Yeah.
Okay. Now in that, I want you to sketch a circuit. And the sketch I want you to draw is number 1, right below it. Okay, you can leave off the switch if you want to. I don't care about the switch. You can put it in or leave it off. But basically, you draw that number 1 circuit up here in the rectangle. Huh? Just do that, yeah. You can leave off the switch if you want to. Draw that circuit in the rectangle. Let me see you when you got it done. Very nice. Okay? Sort of. The only thing that's a little bad about it is you got one more negative than you have positive. So I'll put one. Okay.
Yeah, I did that one more.
Okay. Looking good.
There you go. That's
That very nice. Okay. All right. Anyone else? Okay. I don't see power supply. Okay. Since. Very good. Yeah. I don't agree with that. Yes. Any questions? Very good. Now, by the way. All right. Very good. Okay. And maybe I should have spent a little more time here on the first page. Let's turn back to the first page. Okay? Notice your battery here. Okay? I just happened to notice this when I was looking around. A battery always has alternating long line, short line, long line, short line. What do they mean? The long line is the positive side, the short side is the negative side. And when I saw one that the end lines were both short, I knew something was wrong with that battery. Like maybe it would short out. No, okay. So batteries are represented that way. If you have a ground, which we aren't going to have, that's the symbol for ground. You're used to that. The bulb is basically a resistor with a circle around it, meaning you have glass around it, basically. We're not going to mess with variable resistors. We have an open circuit, meaning the switch is up. And if you did have a really complicated one and wires were going across each other but not connected, you do a little bump on it, like a pregnant Chad. You wouldn't remember that. If they're actually connected, you do a little dot showing they are connected. Okay? So, when you drew your battery, make sure the minimum you have one short line, one long line. If you do multiple cells, then make sure you have the same number of short lines alternating with long lines. The one with the long is going to be your positive side. The one that ends in short is going to be your negative side. All right. Now that one that you've drawn there, what I want you to do is you draw some arrows like we had in one of the slides in the presentation in the PowerPoint, showing the conventional direction of the conventional current and another arrow showing the direction of the electron current. Remember, I pointed that out in class as we did the that in the lecture and when we were doing the PowerPoint. I pointed that out, made a special note of it. So draw your one arrow showing the conventional circuit current and one showing the direction of the electron current. What's that? draw an arrow showing the direction of the yeah, one's going one way, one's going the other. Well, I don't know what they look like. Okay. Okay. Yeah, okay, and which is which? Label the two arrows. One arrow is conventional current, and the other is electron. Not on here, it's in the slideshow. So. Anyone bring a book with them? Okay. Good. Turn it on. There it is. Okay. Does everybody have that? Are there any questions? Be sure you ask questions. You don't want to lose points for just not saying anything or for guessing. You have questions? Ask. Is everybody labeled the conventional current and the electron current? That's all you do on that. You're drawing there. One arrow points one way, one's the other, one's conventional, one's electron. Did you label?
It's not how you write it. It's not how you draw it.
Okay.
That's all. It's not. No, it's not.
You tell me which is one line.
Right like that. Tell me. Listen, Stephen.
Yes. Great. Hey, I'm watching. Okay. Everybody got it now.
Yeah, it's a little opposite way. Conventional current was just the long one.
No, they're going out.
The electron was
The electron current has one that way.
Arrow to the right, conventional.
Everybody got it? This was supposed to be the quick and easy one that's taking forever. Okay.
Well done.
Everybody got it? Any questions? Okay. Number 2 is pointing out a flashlight bulb. Now I've got one I picked out of one of these devices, and I don't know who turned this on. Okay. Here's a bulb. It's not really a flashlight bulb, but it's a bulb. Now, what can you tell just looking at that? Okay. You see there's a metal plate here at the base. Are y'all listening? Watching?
Yes.
Okay. There is a black ring around that, which is actually, guess what? An insulator. And then there's metal around here. Okay. So, on a flashlight bulb like this, you've got 2 wires on the inside. And it's sort of hard to see on this, but there are 2 wires in there. Okay? One of them is connected to this one, and one of them is connected to that. Okay? That way you have a complete circuit with no shortage. That's why you have the insulating ring separating the 2. So, what you have to do for number 2, note the construction of the flashlight bulb. That's figure 20.2 over here on the left of the box. You notice here, you have the filament up here. That's where the current has to flow to heat up and make light, right?
Yeah.
But you don't have any connection here. It's an open circuit. So you have to connect this line to something and that line to something. And let me give you a hint. They won't be the same somethings. Otherwise, you wouldn't be able to get anything to work, right?
Yeah.
Okay? So draw the lines, 2 lines, to make that bulb work.
Draw the lines on the bulb.
Say again?
Just draw the lines on the bulb.
Yeah. Do you have a complete circuit there?
Here?
No, here. Okay, what's missing?
I mean, I do.
No, you don't. Okay, you need to draw some lines.
Say again. Say again. No. Are you talking about right here?
Okay, where would that go?
That's gonna go in here.
Okay, you're hitting glass in both places. That's not going to complete the circle.
Well, I mean, I'm not trying to speak for exactly. But
Okay, let's see. Ah, very good. That is going to the plate down here. I was all the way to touch that another tip, and this one touches another one. That completes the circle. Everybody know what was going on? Let me see. Okay. Not quite. Okay. That looks great. You see? It's going from this around here to that. All right. Everybody see? Yeah, one has to connect to the tip.
Oh, they're for next time?
Are you gonna throw it already?
Okay, everybody see that? Any questions? All right. Now, we begin the real part of the experiment here. Now, I've set up your circuit board for you.
Yep.
Right? Now, on your power supply, whatever you want to call it here, is the voltage generator. It's called a high current voltage supply, a power supply. The little red button in the upper left of the panel, that's your power, on and off. Right now it should be off, right?
Yeah.
When you press it, you'll see the display comes on, and you get zeros there. Should be, anyway. All right. Now, what I want you to do, wait, very slowly, increase that until the bulb gets to be a reasonable brightness. I don't want it too bright. Hey, too bright. Turn it down. Oh my God. Turn it down. You're going to blow my bulb. Okay, that's the reasonable brightness.
Like 30 something.
No. Okay.
Is this too bright?
Too bright. Too bright.
5.5.
Okay. Too bright.
5.5.
5
It's
point.
too bright.
Too bright.
What can you see with that?
That looks reasonable. Right there.
It's not a reasonable light bulb.
Hey, leave it. That's just reasonable. Okay, yours is reasonable. Okay? That's too bright still. Turn it down. Look, you had it 5.5. Why'd you change?
Why'd you touch it?
Okay, it does. Yeah. That's still a little bright.
That is rare. Yeah.
Okay, okay.
Right there. That's it.
Okay. All right. Now, what I want you to do, everybody, look at your bulb. Okay? This is circuit 1. If you look at your circuit there, you'll see this is circuit 1. Going from the battery, your power supply, up through the bulb, and then back to the battery. There's your complete circuit. Notice on the lamp, that line here shows where the current, or you can look at the ugly color there. It shows where the color is. Okay? So you have circuit 1 right there. Now, what I want you to call that is standard brightness. Look at that. That is standard brightness. Okay? If you look at the results on page 181, using the brightness of the bulb from the simple circuit number 1, that's what we have there, as the standard for normal, everything else is going to be compared to that brightness. So get an idea of what that brightness looks like. Okay? Now, what I want you to do is record, and this is where you put your recording. Turn to page 183. You see circuit 1, a simple circuit. What are your observations there? Standard brightness, and if you want to, you can put your voltage there. Whatever voltage you have to create that standard brightness.
So 5.5, right? Or 5.
4.9. Second?
Ours is 5.8.
Okay. Okay. Now, then turn it off. Just on the button. Turn it off. Okay? Now, what you are going to do next is set up circuit number 2. 2 bulbs in series. We haven't talked about the series yet. Yeah.
We know how to.
Two bulbs in series. Now, I want to ask you a question. Where's the wire going in the first time?
Hey, this one's a different board.
Tell me where the wire was going in. Where was it going in the first time? Right up there. And I pointed out to you, it goes through the bulb, follows this line, and it comes out here. That's the wire came out there.
This board, no, it's different than the set training. You got to separate them away.
I don't know why you
more than one wire.
Huh?
How many more than one wire? Huh?
Not really.
People.
Okay, let's leave it just like it is.
This is different than our board.
Okay.
That one's got a bit.
Okay. So there we have that. Now, wait, you don't need it. You could use it if you want to. You will be using it later. But you could use it just from here. You got out from there. No, you have these next to each other. That also. Okay. Got it. Okay. All right. Now, wait. Okay. Everybody set up your board. If not, let me see your board.
Yeah.
Okay, I said before you turn it on. Turn it off. Okay.
It's just instead of the set
Okay.
training.
Yours is working. You got to do that. Let me see. Yours is working. Okay, you use a connection wire. That's fine. Okay. That should work fine. Okay, now. Whoa. Okay? I want you to pay attention. Excuse me.
Excuse him.
Yes.
Hey!
Listening.
Okay. I want you to pay attention to the subtle differences on your figure 20.3 on page 180. Look at your page 180, figure 20.3, that shows these 8 circuits here. Right? You got it looking at it?
Yeah.
Okay. Now notice the first one had, look at the battery. How many plates? 2. One long, one short. What you have in circuit 2?
One long, one short.
That means you have the same voltage. So that means you do not change your voltage from 1 to 2. But what you did change is what? The load. You basically doubled the load, right? You have 2 loads in there. So now, it's okay. It worked before. Okay? Turn on your power supply at the same voltage you did before. And what do you notice about the light? Okay. Everybody got that?
Sure.
Like some people in here future.
No, did you change your voltage?
What is it? Less brightness? Lower brightness? No,
Huh?
no brightness?
Less standard brightness.
There you go. Okay. All right. Now,
Half standard brightness.
okay, folks, listen up.
One half standard brightness.
Listen up.
Listening.
Okay. Now, y'all listening?
Yeah.
Okay. What your observations are from now on. The first one was just standard brightness and your voltage. Your observations from this point on are going to be one or both of these two features. The first one, is the bulb or are the bulbs brighter, dimmer, or the same as standard? That's your first. The second is, what happens to one bulb when you remove the other bulb? In other words, take out one.
It's not
Well, do it and see it. And what happens?
It doesn't work.
It goes out. Okay? So those are the two observations you make every time.
So you
If you've got two bulbs, are they brighter, dimmer than standard, or the same as standard? And number two, what happens if you take one bulb out? Okay? What's that? You could say that. I'd say just dimmer, brighter, or standard.
You shouldn't have wants to be exact.
Huh?
He wants to be exact.
Well, it may be close, but it may not be exact. Because the brightness is a 1 over, it has a little bit difference in it. Okay? Okay. So if you got that one done, then set up circuit 3. What do you notice about circuit 3?
Hold on when you get there.
2 batteries in standard.
Okay.
So it's twice
Okay.
the load, or not twice the load, twice the power.
With one
From
bulb.
what?
What?
From
battery. From standard.
From your number 1.
So that means we need to do
Okay,
10
so
volts.
go back to number 1.
Back up to it.
Set it up. Now here's what I do not want you to do. Are you listening?
I'm listening to you.
I do not want you to double the voltage, even though that's what it looks like it. I want you to just barely increase the voltage, just enough for you to tell if the bulb is going to be brighter, dimmer, or standard. But don't double the voltage. You'll blow out the bulb. Okay, that's enough. What can you tell? What can you tell?
It's brighter.
Brighter. Okay?
How about that?
Okay, turn it off once you determine.
Yeah.
Okay? And there aren't two bulbs, so there's not removing the second bulb. Okay? There's only one observation on that. Brighter, dimmer, or standard.
Circuit 3 is just one.
Okay, have you done circuit 2? Huh? Okay. Yeah. Okay. Do circuit 3. Remove one.
Circuit 3.
Back up on
2
12.
volt series. Right.
Turn it off.
2 batteries. My bad. My bad. Oh, man.
Now, don't double the voltage. Increase the voltage slightly. That's enough. What happened when you increase it? Okay. You convinced, right?
Yeah.
Okay. So that's all you put down for number 3. Okay. Now, circuit number 4. What's different with that?
It's 2 volts in series, 2 batteries in series. Dimmer, something like that. It's going to be dimmer.
Y'all keeping up?
How much volt do what? 2 volts in series with 2 batteries. 2 volts in series, 2 batteries. You can do what?
Remember 2 volts, 2 things.
Think about what you're saying.
Go back,
Look at it. Think about what you're saying. Get it wrong.
Go back to number 2.
2 volts in series with 2 batteries. In other words, you would double the voltage.
Oh, it's going to be as bright as the standard voltage and the current supply.
No, it would be the same brightness, but twice.
So is it going to be, if you had it at, if you don't increase voltage, current, it's going to be brighter because a bulb is going to require so much more.
No, whenever you increase the batteries.
Well, see, it's going to be dimmer than what we just had, but it's going to be close to standard.
It's going to be the same as standard. It's going to be the same as standard. Same as standard.
Hold on, turn it off for a moment. Okay. Go back to your original voltage. Turn it off. Is that your original voltage? Okay, yeah.
So now we need a parallel.
Now. Okay, now, what can you tell me about the brightness? That's sensitive. That's different than the standard.
Because
That's what I said. Look carefully at that person. That's different than standard.
I forgot what you said. And then it's like, oh, my yeah, see, and then on the two batteries. On the two batteries, that
So
one.
that's what we put on this number. Not
On
standard.
circuit 3.
Number one was standard.
On circuit 3. On the same flash. Higher than two batteries would be standard.
Now, you're on number 3 now? This time I did want you to double the voltage for your original one. For only one bulb I didn't, but this one you want to double. That was on one bulb. That would get too bright. This one I said, I hadn't said yes, but that's why I didn't want y'all to get ahead on me. So you double the voltage.
Okay, so we about standard brightness.
Well, see it.
We already done.
You did the same, double the voltage.
He does it anyway, but he just
Okay.
I just lied to you, okay?
You don't
I lied to you over there.
All right, well, I'll go grade what you turn in. I'm here for you to check it, let me check it. And I can make sure you're doing it right, or you can do it on your own. That's fine. Well, no, don't get ahead. Okay. So number 4, this time I do want you to double your standard voltage. I didn't want you to do that on 3 because it would get way too bright. On number 4, you got twice the load, so you could double it. Did you double it?
Yes.
Okay.
Can we
And
do
you
it
got,
again? So you
oh no. Okay. And what happened? What 2 observations did you have?
Same as standard brightness.
That's one observation.
When you remove the
Double
other
voltage.
it's gonna go, it's not gonna work.
Okay. The other light goes out. Okay. Remember, if you got 2 bulbs, you've got 2 observations, right? One is the brightness, and the other is what happens if you remove a bulb. Okay. So has everybody done number 4?
Yes.
Have you got something to record on? What do you think about the brightness? Yeah, I think so too. What happens if you remove a bulb? Goes out. So put that down on your observation for number 4. Okay. So everybody has done number 4, right?
Right.
Okay. Move on to 5. What do we call 5?
Parallel.
What's parallel?
The circuit.
The loads are parallel. Not the circuit. The load's parallel. Whoa, turn that down.
Hey, that's not that bright.
Okay.
Pop all these bolts.
Okay. All right.
Not
What have
supposed to
you
be
got
swearing.
You got it set on 4.9? What do you
Yeah,
got it set on?
4.8. Yeah. What do you say about the brightness?
Standard brightness.
Okay. What happens if you remove a bulb?
I don't think that is.
The other one will stay on because
The other one stays on. Exactly. Now turn it off. Okay. Get the
Got that.
Okay, everybody got number 6 done? Everybody done? Okay. Now, before any of you do number 6, on number 6, I do not want you to double the voltage. I want you to increase the voltage slightly. Okay?
From 9.8 or 4.9 or which?
No, don't double the voltage. Increase it slightly from your 4.9 from your original. Otherwise, you don't blow bulbs, and I don't want any square bulbs. Okay?
bulb stays on.
Okay, what are y'all doing now?
We're going to increase it about 7.
6. Okay, you
stays on.
Okay. So what was the difference between 5 and 6? Yeah, 6 was right. Okay. Now number 7, I don't want you to set up the thing. I want you to think through that one.
Think?
Yes, I'm sorry. Okay. Asking a lot. I want you to look at number 7 and tell me what you see. Okay, don't set it up.
This isn't going to work.
No, why not?
Because you're going to be.
You said one ball in parallel. You can't have one ball in parallel. It'd be series. That'd be a series circuit.
Okay. What you have there and what they. Okay. On number 7, folks.
You're going to blow the
Is
ball.
everybody listening? Number 7. I'm trying to find it here. Oh yeah, number 7 on page 183. Notice what it says for number 7. One bulb in parallel with a wire. Problems there. Show with arrows how the current takes the path. Okay, a lot like a student, right? Okay, good.
Yeah, short. That creates a short.
What's that?
Creates a short.
Exactly. That's what we call a short circuit. What do you notice about a short circuit?
Doesn't work.
Yeah, the light doesn't come in. Oh. What about an open circuit? It doesn't come on. So are they the same?
Yes.
No.
In some ways.
Come on. A short circuit, the current is going somewhere, but it's not through the light. It's going through the wire, which has less resistance. The path of least resistance, right? Okay? Where an open circuit, the current's not going anywhere because there is a break in the current. So they have the same result, but very different reasons.
I want to show that with an arrow.
Okay? Go back to your picture here, or you could draw it again. This picture here, show where the current will go in that. Yeah. Okay? Here's a jumper. The current has a choice. It can go this way, that way, or both. Which way does it go?
It's going to go just through the wire.
Just through the wire, because there's more resistance in the bulb, so it's not even going to begin to go through the bulb. Where do you want to draw the arrow that goes through the wire? Okay, that means you increase the voltage. I said don't double it, increase it. And the other one, so turn it off. What do you notice about the brightness? Increase, okay, brighter. And then what's the other thing, observation you're to make? Take one out. What's going to happen? Yeah, the one stays on. There you go. Turn it off once you've seen that so you don't blow up my bulbs. Yes.
I just put here, so it goes on, so it goes across the road to the fire.
Okay. But put an arrow where the current is. Show with an arrow how the current takes the path. Where does the current's going through the wire? I'll show you here. Here's the current going right there. Okay, where's it going up there?
Up here?
Not there.
Here?
Yes.
Instead of on that one.
Okay, but it's going through the wire, through the bulb.
The wire.
Okay, well, you put the arrow on the wire, not the bulb. Very good. Yeah. So it goes that way. Okay. Okay. But the current usually is indicated with the arrow. Okay. But here's the junction here. Okay, that's the wire here, right? Okay. There's your light bulb. Which way is the current? Yeah. That's it. Got it. Okay, don't do 7. If you try to do 7, we're going to have a melted plastic around the wire. Yeah, I don't want that to happen. Okay. All right. Had everybody done number 6? Yay or nay?
Yeah.
Okay. Now look at 8. And except for how the wiring is done and the switches, that's exactly like which one?
Exactly like the third one.
Third? 3 only has 1 bulb. No parallel. 5.
The sixth one.
It's just like 6. You're absolutely right. So you can either remember what 6 was. Do you already have it set up there? Do you write the same thing with 8 as you did 6? Oh, it's the same thing. Just put an extra switch in there. And we're not doing switches.
So what about number 7?
7. Okay?
You said that.
Okay.
6 and 8 is going to be the same thing.
Same thing. Okay, number
And
7.
we draw this one?
Yeah, number 7. Draw. That. Over here. Okay? And with the arrow shows where the current is going. Okay? Yeah. Number 8, except for the switches, just like
But yeah, that's how Willie feels. Every year.
Start.
That's how Todd feels.
Absolutely
Every year.
Same pattern.
Imagine that. Every year.
Parallel.
No, it said draw.
Huh?
Every year.
It said draw.
Well,
For 7.
Now we understand
6
why
is 8.
Todd got to the point where he was like, this is motherfucker. They're in the front and back.
7, you draw this piece to show the current.
so you did
7.
yeah.
You can't do cursive?
You draw this.
Dude, seriously? Alright, that's how it happened in my school. They taught us like cursive, and then I started trying to use it and like learn it, and they're like, no, you can't write cursive. Should be 145.
Yeah, that's what I was.
Yeah, I never write it. I used to. Dude, I used to write everything in cursive. And then I got mad.
Except for the switch.
I don't know if he's talking about that relevant the way it was, so but we really couldn't.
Okay. Now my question to you is, do you have all the observations you need on page 183?
Yes.
You've answered brightness
Yes.
on all 8 of those. And on the ones with 2 bulbs, you've answered what happens if you remove a bulb, right? Everybody?
Right.
Okay. Now, are you listening?
Yes.
Now what you do is turn back to page 181 on results. Okay? And using what you wrote down on your table on page 183, you answer the questions under results. Okay? Now, I want to point something out to you. Number 1 is just join a team, any team. Okay? Okay? On the results number 1, listen up. Results number 1, using the brightness of the bulb in the simple circuit as standard for normal, describe which circuits had bulbs with normal brightness. That should be recorded in your table 20.1. To report, that's all you do on that. List the number of the circuits that had standard brightness. Okay? Now, you can do it later. I'm just telling you what to do. Number 2, look at that. Which circuits had bulbs that were dimmer than normal? But there's another little word there. Explain. So number 1, you're just going to write in the number of circuits that had standard brightness. Number 2, you write in the ones that were dimmer than normal, but you have to say why. Number 3, which were brighter than normal. Explain. So you have to do 2 answers for number 2, number 3, number 4, and number 5, because all of those had explain by it. Right? Understood? Number 6 says give the general requirements for any circuit to function. And number 7, you can answer it however you want, but if I don't see an answer, some sort of answer, you get it marked wrong. I mean, you don't get credit for it. Okay? Any questions? Okay. Now, can y'all work on that for a bit
Yes.
by yourself? I've got to run down and get 2 evaluations done by adjuncts. I'll be right back.
We still have a test today.
Second?
We still have a test today.
Yeah. But you got some things to work on while I go. I'll be right back.
Yeah, I think number 2.
Only wish. 2 and 4. Right?
What you got? You on 3? 3 and 6. Four, 5, 6, and 7. 4 and 5.
Well, this is what bowls and pressure things people use in other countries, like your Eastern country, they smash themselves up and make food and sauce.
No, seriously, I put 20 volts in that thing. It didn't go on. I think it's going to be okay. 4 volts. You okay? You good?
Just hear you from across the fucking campus.
What are you doing,
Are you saying that you bring
your meat
Rosie? Okay. It doesn't hurt my hand. It should. Hard is sometimes when you get every report card.
You're busy.
You're gonna get
Don't put ground. Don't have a ground on that. No, that's not a ground. That's negative. We're going from positive to negative. That's what he was fucking saying earlier. That's why I was getting frustrated. He was saying it needs to be ground, but really it's not a ground. It is a close circuit to the battery. It's not a ground. It's a true ground. A true ground is when you have a wire to the ground. And the electricity that goes to it flows to the ground. Literally to the ground. I'm just
Yeah.
Want somebody with no shoes on.
no, then it's going to a ground. Period. But I'm just telling you what he was saying earlier. So put the ground on it.
What's really sick? Then describe the general requirements for any certain thing. What would he want us to write?
What was the purpose of this landmine?
I
was not paying attention.
I really don't care. Yes, for teaching basic circuit knowledge.
Yeah, one goes out and one says left.
One, he asked, was the purposes of lab knowledge? I said yes for teaching basic circuit knowledge. Just to make it happen.
Great experience.
Oh, it makes me feel good, Jared. I wrote the same thing.
Oh, thank you. I was worried you were going to say
No, for real. I put like 26 volts on stuff. Stop.
Oh, hey.
I'm trying to correct his words. I wrote that because that's what you said. Negative 5.
7's wrong.
7.
Wrong.
What'd you put down for 4?
Oh, you said 7. Oh. 2.
You didn't even have to.
Okay, I don't even know what I'm doing.
No, I said it loses negative path. He's talking about negative path. took a crown.
Creates an
Hey, did they even send around grocery marshmallows?
Like 25 points on these. You know that.
Yes. Is your name Chris? That's what I thought. I thought it was like
Something. I think it's Chris.
oh, what is your name?
I think he did.
What is your name?
It is Chris. It's on his fucking paper. His name was Chris. I said, I looked on the fucking roll.
This is Yale. Yale racing. His name is
What'd you cook for number 5?
Where'd my life go?
Yeah, it is. It's Chris. Chris Williams. Told you.
Well, I mean, I'm just saying, which circus did you do?
5, 6, 7.
You blame me, dude.
Just work it out. That's bad parenting right there.
Don't worry.
It might be,
Y'all think you shoot this one?
Yes.
It's not hard.
stay out.
Where? Here.
So you know it is about like that. Stay out.
Stay out. That's games you use.
Yeah, you can customize your own controller.
On Xbox or on Microsoft. It's like, it's not as cool though. That's weird.
Okay, how y'all doing?
Swell.
Okay.
Where's this go?
Okay.
Why he got his backpack on like
I have a
test? You have a test.
I don't think we're staying in this class, are we?
We are.
No, we're not.
Yeah, everybody got it? Anybody have questions?
Let's do the test right here.
Any questions?
Let's go. I'm gonna say mine too.
Okay.
Right here.
I mean, no, it does look like a cat got it on your neck or something.
What?
Looks like a cat.
Oh, that? I don't know what that was from. I don't know. I guess if I got choked in my sleep or something, something wrong.
Okay, I think all of them are, but be sure your power supplies are turned off. Right? Yes, thank you.
He knows the expectations with him and his boyfriend got. You talking about that the other day? How much you talking about?
You want to go back to the classroom, you can, as soon as I get everybody. Okay, if there's no more questions, I'm going to shut down the record. Hey, leave the brains alone, okay? All right. Okay, somebody left something pinned to the board. Hunter?
I think that's actually Andrew's fault.
Okay, well, someone needs to take it down.
I'll tell you what, I'll take that.
Okay, that's excellent.